Okay, in chapter 9, I talked about, and your book talked about, using different bivariate statistical tests to conduct hypothesis testing. And generally, bivariate statistical tests, although sometimes in research they are the only tests used, more typically it's a preliminary test to see if the independent and dependent variables, two variables, are associated. Remember that these there has to be at least a statistical association between the independent and dependent variable in order for the variables to be causally related. And that should be familiar to you from back in research methods. Again, the specific bivariate test you use depends on the level of measure of your independent and dependent variable. So here, if both your independent and dependent variable are categorical, meaning either nominal or ordinal, then you use a test called the chi-square test. And sometimes you'll see it abbreviated. The symbol kind of looks like a fancy X with a squared sign, and that's chi-square. So make sure that you know that. If the dependent and independent variables are both categorical, and remember categorical variables are nominal or ordinal, they are the variables with categories, then you use a chi-square test. You also should understand the difference between statistical independence and statistical dependence. This should be pretty straightforward stuff. So if the independent and dependent variable are not related to one another, they are independent from one another, they have statistical independence. If that's the case, if the independent and dependent variables are not related or they are statistically independent, you would fail to reject the null hypothesis, meaning you couldn't reject it. You would have to accept it and say there is not a relationship between these variables. Conversely, statistical dependence is when the independent and dependent variables are related, which means that the category of the dependent variable can be predicted based on the category of the independent variable. So if the two variables are statistically dependent, you would reject the null hypothesis and retain your research hypothesis, or you would say that your research or the alternative hypothesis is supported. The independent and dependent variables are statistically dependent. They are related. So now I'm going to go through a chi-square step by step. Make sure that you can do this on your own. It's important. There is an example in the book that starts on page 207, and it does the same thing that I'm about to use. I'm just going to use a different example. I'm going to try to explain step by step what the book does. If you understand it, great, then this is just going to reinforce it. If you don't understand it, hopefully it will make a little bit more sense. And if you kind of thought you understood it, but it seemed overwhelming, hopefully this will kind of simplify things and make you realize that, again, these formulas look really complex and intimidating, but most of them are nothing more than addition, subtraction, multiplication, division, and taking the square root or squaring something, which squaring something is just multiplication anyway. So you're not getting into any sophisticated math at all. You just need to understand what the symbols mean, what the numbers mean, and how to obtain them. So I'm going to go through, I just made up my own example. I'll go through it. I also would recommend that there are review questions at the end of every chapter. The answers to the odd numbers, I believe, are in the back of your book. I don't think I have the instructor edition of the book. I think that I have the same edition and the same book that you guys have, and the answers to the odd questions and at the end of chapter reviews are in the back of your book. So I would recommend definitely going through the odd questions and then looking up the answers to make sure that you're getting it. And then if you want just additional practice, then maybe go through and do some of the even questions. And if you do even questions and you're like, hey, can you check number 2 for me? Or can you calculate number 2 and give me the answer? I'm happy to do that. Just let me know if you ever have specific requests if you're doing the even review questions. I would prefer that you do the odd ones first because you can look up the answers, and then in addition to that, if you end up deciding to do the even numbered questions and want the answers, let me know and I can calculate them and give them to you. Okay, so I'm going to show you a chart that I made. And again, it's similar to the chart in your book. It just has different information because it's a different example. So you can see that my dependent variable is political affiliation, which I measure as conservative or liberal. So my columns are conservative and liberal. And then there's the column marginal, which is just the total. And then my independent variable is race, white and non-white. And clearly there are different ways that you can measure these concepts. The A, B, C, and D are the cell. So like cell A shows you, see, I'm looking at this backward. Cell A shows you that there are 66 white conservative people. Cell B shows you that there are 34 white liberal people. Cell C shows you that there are 42 non-white conservatives. And cell D shows you that there are 58 non-white liberals. So my prediction, my research hypothesis would be that non-whites are more likely to identify as liberal than whites, and conversely, whites are more likely to identify as conservative than non-whites. The null hypothesis, the hypothesis of no relationship, would state that there is no relationship between race and political affiliation, that you could not predict someone's political affiliation based on the category of their race. This is about as straightforward as an example as you're going to get because it's a 2x2 category. I mean, you've seen like in your own research, you know, if you have 3 categories, which I required you to have for one of your independent variables, and then a 5-category dependent variable. So if you had like a Likert scale, like if you were predicting death penalty attitudes, or if you had categories of sentence length and there were 5 or 6 categories, then you can see how, you know, this chart is 2x2. There's 4 cells. Hopefully you can see that. Yeah. There's the 4 cells, and then you see the row marginal, which again is just the total, and then the N, which is the sample size. Now I lost my train of thought. Sorry. So you see how if you have more categories, so you could have a 3x5 chart. So you could end up with 15 cells. You could have a 6x6 chart, which would be 36 cells. That gets really cumbersome to interpret. So statistically, yes, you can do that. You have 2 categorical variables. So if you had a 5x6 chart, you had, let's say, 6 categories of race to measure race, and then a 5-category Likert scale. You could do that. You could run a chi-square test, and you could say, yes, there are significant differences. The chi-square is significant. But then you get into, well, which category is more on the independent variable is more likely to fall into which category of the dependent variable. And that gets really, really cumbersome. It's difficult to interpret. And it's just more complex than in most cases than it needs to be. So typically what you'll see researchers do is they'll recode. So like if you're looking at, let's say, the effect of race on attitudes toward capital punishment, and you need to measure race using a valid measure, so you might use the census measure. And they'll say there's like 6 or 7 categories in the census measure of race. And I don't remember all of them. It's like white, black, Hispanic, non-white, and they've changed this so many times too, I can't keep up with it. They used to actually separate race and ethnicity, and I don't think they do anymore. American Indian or Alaska Native, Asian, other, mixed race. So there's a bunch of different categories. So you have, let's say, 7 or 8 categories, and then 5 on your dependent variables. So it's a question, to what extent do you support or oppose capital punishment? 1 is strongly opposed to 5 is strongly support. Then you have, let's say, a 7 or 8x5 table. So you're looking at 35 or 40 cells. Researchers, nobody wants to deal with that unless they absolutely have to, and that's pretty rare. So what a researcher might do is say, look, I expect people who are non-white to be less supportive of capital punishment because non-whites in this country at some point or another typically have had some history of oppression. Different types of oppression, different experiences, different time frames, different levels in terms of intensity, different lengths of time. But generally, when it comes to, we're looking at trying to predict attitudes toward capital punishment, and given that purpose, basically just the fact that there is some history of oppression, the non-white groups tend to be less supportive of institutions like capital punishment for that reason. And you would cite literature saying that, and it's out there. So you would say for this reason alone, and it's not just my opinion, I have evidence to back that this is probably going to be the case. I'm going to recode, and any whites stay in their own category, and any of the non-white races or ethnicities get combined or recoded into another category. So now you're just looking at the differences between whites and non-whites in terms of their attitudes toward capital punishment. You also can recode your dependent variable. You can just recode your dependent and not your independent variable. So you as a researcher would need to figure out, okay, I don't want to look at 40 cells of information or 30 cells of information. How can I get this and simplify it, but still have it be meaningful? And you might say, like with attitudes for capital punishment, maybe you break it into 3 categories: support, neutral, and oppose. So then you have a 3x2 table. But again, it depends on theoretically what you can justify doing. So that would depend on what your variables are and what the nature of the relationship is that you're looking at. And you as a researcher would make that call, and you would need to justify it. Here, we're keeping things simple. In your own project, I kept things simple. You do need to do a recode of 1 variable, but that would be it. And that's honestly just to show, it's to simplify things for the chi-square, but also because I want you to know how to do a recode in SPSS, and I want you conceptually to understand what that can mean. And even just consuming research, if you're reading about findings from research, it should raise questions. How did they measure this concept? Did they recode it? And if so, how and why? So just, I think, an overall enhancing awareness also. So make sure that you understand statistical independence and statistical dependence. I'm now going to go through this chi-square step by step. You're going to see these same 5 steps, or very similar 5 steps, for all of the bivariate statistical tests. So they're going to be slightly different, but the general step is going to be the same. So the first step, you're going to state the null and the research hypothesis. Well, here you're going to state it specific to chi-square. So the hypothesis for my example would be that there is no relationship between race and political affiliation. In other words, chi-square, the difference is 0. My research hypothesis, which I stated before, H1, remember H sub 0 is the null, H sub 1 is the alternative hypothesis or the research hypothesis. Whites are more likely to be conservative than non-whites, and conversely, non-whites are more likely to be liberal than whites are. That's step 1. Step 2, identify the distribution and compute the degrees of freedom. The degrees of freedom and the formulas in your book, you don't need to memorize it, but it's a pretty easy one, but with so many formulas, I could see how you wouldn't remember it. You just take the number of rows minus 1 and the number of columns minus 1, and then multiply those 2 numbers. So R minus 1, C minus 1, R is just the number of rows, and C is the number of columns. You do not include the marginals as a row or a column. So going back to this example, hopefully you can see that. I have 2 columns, and I have 2 rows. You do not include the marginals. You're just including the substantive information. So you're looking at whites and non-whites and conservatives and liberals. So rows, number of rows is 2. Minus 1 is 1. Now the number of columns, 2 minus 1 is 1. 1 times 1 is 1. So my degrees of freedom equal 1. Now, if I had conservative, moderate, liberal, instead of just conservative and liberal, then I would have 2 minus 1, because I still have 2 rows, which are whites and non-whites. So 2 minus 1 is still 1, but I have 3 columns. Now, if I had conservative, moderate, and liberal. So 3 minus 1 is 2. So 1 times 2 is 2. So if I had a 3rd column, I would have 2 degrees of freedom and not 1. Step 3, you're going to identify the critical value of the test statistic and state the decision rule. Don't let the language get overly complex for you. You have the information you need to do this. You need the degrees of freedom, which we just calculated. The degrees of freedom in my example is 1. And you need alpha, which you as a researcher set. As a researcher and in criminology, criminal justice, our alpha levels that we typically use are 0.01 and 0.05. This has to do with what what is the risk that we are willing to take that we are wrong? And if you convert those into percents, 0.01 is 1% and 0.05 is 5%. Typically, 0.01 is pretty low. The most typical alpha that I see is 0.05. So you'll see if P is less than 0.05, then a relationship is statistically significant. That's why we're basically saying as long as the probability that we are wrong is less than 5%, then we're willing to say we're probably right. Occasionally, if you have a really small sample size, you'll see researchers raise the alpha to 0.10 because it's harder to get a statistically significant effect with a small sample size. So then you'll see researchers say, I moved the threshold, we're willing to accept a 10% risk of being wrong because the sample size affects things. Conversely, with really large samples, almost anything can be statistically significant. So you'll see researchers at that point often lower the level to 0.01. But for just kind of traditional samples and sample sizes, usually we set alpha at 0.05. But again, you as a researcher, so you need to know alpha for step 3, you as a researcher choose that level. And like I said, typically it's 0.05, sometimes 0.01, more rarely, but occasionally it's 0.10. Once you have those values, you find their intersection at the chart, which is in Appendix D in your book. So we have the degrees of freedom at 1. I'm choosing the alpha of 0.05, and I ended up with the critical value, and I looked up at, just find their intersection. It's a grid in Appendix D, and my critical value is 3.841. So now the decision rule is that in order for my hypothesis to be supported, so in other words, in order to reject the null hypothesis of no relationship, the obtained value of chi-square, which we're going to calculate next, must be greater than that critical value, which is 3.841. So if the obtained value of chi-square is greater than 3.841, we are going to reject the null in favor of the alternative hypothesis. So step 4, we're now going to compute the obtained value of chi-square. Chi-square is the difference between the observed and expected frequencies in each cell of our table. So the observed, they're the numbers that are in the table. That's what we are observing. They are there. The expected values are the values that would be there if the variables were unrelated. So if the null hypothesis was true, what values would we see there? And that's what we need to figure out. Because if those values are the same as the values we have in there, then we know that we cannot reject the null. So now we need to compute the expected frequency for each cell. So you take the row marginal times the column marginal and divide it by n, which is the sample size. So for my example here, and because I used the number 100 for both, my example looks like it's a little bit different than the one in the book. It's actually not, but you're just going to see because I have both whites and non-whites, I totaled them to be 100. I just, for sake of easy numbers. So that's why you're going to see some repeats that normally you wouldn't see. So you do this for each cell. So I already know that I have cells A, B, C, and D. If I had had conservative, moderate, liberal, I would have A, B, C, D, E, F. And I would have to do 6 calculations. But these are easy. So all you're doing is multiplying and dividing. So the row marginal, so for cell A, the row marginal is 100. And the column marginal is 108. Hopefully you can see that. So you take 100 times 108 and divide it by the sample size, which here is 200. So I did this calculation. I took 100 times 108, and then I divided that number by 200. Cell A, the expected frequency is 54. The observed frequency is 66. Cell B, the row marginal is 100 times the column marginal, which is 92. I divided that by 200, and I got 46. So the expected frequency in cell B is 46. The observed is 34. Cell C, it's the same as it was in cell A. The row marginal times the column marginal, it's 100 times 108 divided by the sample size, which is 200. Again, that's 54. And then cell D, which is the same as cell B, again, because my whites and non-whites, I have the same number of them. So 100 times 92 divided by 200 is, again, 46. Once you have those numbers, you take each cell's observed minus expected frequencies. Do not just put the bigger number first. It's observed minus expected. So for cell A, it's 66, which is the observed, minus 54, which was the expected, which is 12. For cell B, it's 34, the observed, minus 46, which was the expected, which is minus 12. For cell C, it's 42 minus 54, which is minus 12. And for cell D, it's 58, again, the observed, minus 46, which was the expected, which is positive 12. Then you square each one. So cell A, 12 times 12 is 144. For cell B, negative 12 times negative 12 is positive 144. Cell C, 12 times 12, 144. And cell D, negative 12 times negative 12 is 144. You divide each of those by the expected frequency. So for cell A, it is 144 divided by 54, which is 2.67. Cell B, 144 divided by 46, which is 3.13. Cell C is the same as cell A, so it's 2.67. And then cell D, which again is that 144, which is the squared, 12 squared, divided by 46, which is the expected frequency, is 3.13. Then you add those numbers. So you add 2.67 plus 3.13 plus 2.67 plus 3.13, you get 11.60. So my obtained value of chi-square is 11.60. It's a little bit time consuming, but all you are doing is adding and multiplying numbers. You do not need to memorize this formula. So if you think, oh my gosh, like how on earth am I gonna remember what I add, what do I divide by, when do I square things? Don't even give that a second thought. You will be able to look up the formulas. I wouldn't even say, oh, make sure you write them all down. You will have plenty of time to look up and apply the formulas on assessments and on your final exam. If you don't think you do, please let me know. I think I gave you plenty of time, but again, if I'm wrong, please tell me. And especially if like 5 of 8 of you or 6 of 8 of you are like, look, I ran out of time in the middle of the chi-square, then tell me and I'll definitely make sure I fix that. But I think that I gave you guys plenty of time to run these calculations. So do not worry about memorizing formulas. Okay, so that's step 4. So you now have the obtained value of chi-square, which is in my case 11.60. The final step is then I'm going to make a decision about the null and state the conclusion. So here, 11.60, which is my obtained value of chi-square, is greater than that 3.841, which was that critical value. So we are going to reject the null. And we can see from the table that consistent with our expectations, non-whites are more likely than whites, hopefully, yeah, you can see that, to be liberal, and whites are more likely than non-whites to be conservative. We know that a weakness of the chi-square test is that it can be more difficult to find a statistically significant relationship for smaller samples, and then for very large samples, most relationships are going to come out as statistically significant. And I mentioned that before. Once you have a significant relationship based on chi-square, you don't know whether that relationship is strong, moderate, weak. So to make that determination, you need to look at measures of association, and that's what your book goes into it in the final part of the chapter. You only look at those measures of association if you reject the null after you run that chi-square test. So if you find out there's no relationship between the variables, then you don't look at the strength of the relationship because there is no relationship. Starting on page 218, your book talks about different measures of association, which again, you look at those only if you have a statistically significant chi-square, and it talks about what to use when, and that just depends on whether your variables are nominal, ordinal, a combination of the two. And again, I've mentioned this several times now, it would be helpful if you had a chart of what measures you would use when, but don't spend a ton of time on these. Especially the measures of association. If you look in SPSS, if you haven't already done your project, you'll see, like when you click the chi-square statistic, right below that is the measures of association, and they're actually broken up for you. Nominal, the list of measures, ordinal, the list of measures, and then there's some other category where you can check things too. So you need to be able to draw on the information, and you need to know that you would need to look for the information. So if you have a statistically significant chi-square, then yeah, you would need to know, well, in order to figure out how strong that relationship is, I know that I need to request measures of association, and I need to be able to interpret those. But as far as memorizing, when do I use lambda versus Kendall's hobby versus phi versus this. I mean, there's so many of them that don't stress yourself out over memorizing, and definitely don't do that for the final either. I'm not going to ask you questions. Well, if you have two nominal variables and a statistically significant chi-square, what test would you use? What measure of association? I'm not going to ask you that on the final. So it would be helpful if you had a chart to just draw on it very quickly, but you're not going to be tested on memorizing that kind of thing. And as I mentioned, when you carry out data analysis, then you would request the appropriate statistic and you would interpret that output. And you're going to do that in SPSS. SPSS calculates almost all of those measures of association. I don't think SPSS does the proportionate reduction in error, the PRE, but it does most of the big ones. And if you ever did need to use the PRE, you could look up that formula and figure it out. So I'm more concerned with, would you know when to use the different measures? Do you know that they exist? Do you know what their purpose is? Things like that. I hope that this made sense to you. Again, go through, hopefully me taking you through this helps some. Go through the example in your book, practice, look at the odd questions in the review at the end of the chapter because the answers are accessible to you. If you feel like you need any additional assistance, please come talk to me. And I will be putting together a study guide. I'm going to make up your final and then put together the study guide from the final so I can ensure that the two are consistent. If you have specific questions, I would recommend, starting to put together a study guide now. It will help with your end of chapter assessments too. So as you're doing things like that, if you're doing things like that and you have questions or need advice or anything like that, please get in touch with me. I'm happy to help you however I can. So just please let me know. If you're struggling with the material or putting together a study guide, or you need answers to the end of the questions or the back of the chapter stuff, anything that I can help with, just let me know.